In this chapter called electromagnetic induction, we're going to learn about how to generate electricity. So to generate electricity, we are going to examine two laws, which is Faraday's law and Lenz's law. And those two laws govern the generation of electricity. But in their laws, they will mention some terms which we have to learn first. So we're going to talk about what is flux linkage, what is cutting of flux, what is change in flux linkage, because they always refer to this. So let's talk about what is flux. Now, if you could imagine the magnetic fields, right, you will actually can draw some lines to represent them. So imagine these are your magnetic fields, right? So we used to have this formula in the previous chapter where we talk about F equals to BIL, remember? And you get B equals to F over IL. So this formula gave us the definition of flux density. We called it force per unit current in a conductor of unit length. Okay, so something like this. But then there's another way of looking at flux density. If, for example, we could imagine or draw the lines here to represent the magnetic field, if we could count them, that would what we be called flux. We can call them flux. So flux density, another way of finding how strong the field is, or we call it magnetic flux density or magnetic field strength. If you could count the number of lines here and you divide by the area it's passing through, which is this, then that could also tell you how strong the field is. Because the more lines you have in the same area, that means the stronger it is. So therefore, this is called flux. And the formula for flux, if I were to rearrange, make flux as a subject, I will get flux equals to BA. So the definition of flux is this. Product of the flux density in the area when the flux is at right angles to the area. And therefore, the unit for flux is called Weber. So 1 Weber, by definition from this formula, will be the flux density of 1 Tesla exists at right angles to area of 1 square meter. So 1 times 1 gives you 1. Okay? So that is called flux. Okay, and the unit will be Weber. So if you want to define flux, you use here. When define flux density, we still have to go back to our original definition. So don't define flux density from this equation. Okay, now let's talk about what is flux linkage. Now, if I had let's say example, if I could draw maybe 3 flux lines here, example, and I had 2 coils, coil A with 1 turn and coil B with 3 turns. Okay, now the number of flux lines passing through each of them is the same, because can you see there are 3 flux lines passing through them. So if I ask you for the flux in coil A, you will say there's 3. Example, we could count them and get 3. And the flux in B also 3, right now. Okay, but then if we talk about flux linkage is actually the number of flux in each turn added up together. So the formula for flux linkage will be N phi, number of turns times the flux. So if there are 3 flux here, but there's only 1 turn, so then the flux linkage will be 1 times 3. But for the other one, coil B, the flux linkage will be 3 turns times 3 flux, so you get 9. So that is what we call as flux linkage. So it's not the same. You got to count the number of flux in each coil, then you add up all of them all together. So the formula for flux is here, just now I gave you, which is flux equals to BA here. So flux linkage will therefore be N phi, which is a symbol for flux linkage, equals to NBA. Now do not cancel the 2 n's here, then you won't get flux linkage. Flux linkage, the symbol is N phi, so therefore the flux linkage is NBA. Unit also Weber. Alright, so this is what you mean by flux and flux linkage. Now you also need to be able to describe some experiments to show how electricity is induced. So there are 3 experiments that you can talk about. So I'll show you these 3. So I'll explain to you the procedure and the observations, but the explanation will come later after we've learned the theory. So let's talk about how to generate electricity. So one example is using a motor. Okay, if you're using a motor connected to a voltmeter. Normally, a motor, if you connect to a power supply, when you turn on the switch, current flows and it starts to rotate, right now. But now we connect the motor to a voltmeter, not the power supply. We use our fingers to rotate the shaft. So when we rotate it, we notice the voltmeter shows a reading. That means you're generating electricity. So there will be two observations. So you will notice that the faster you spin the shaft of the motor, the higher the voltage. That's the first observation you need to say. The second observation, you notice that if you turn it clockwise, let's say the voltmeter deflect to the right. If you rotate it anti-clockwise, it will deflect to the left. It's always opposite. Okay, so that is later we explain why, but these are the observations. Another example of generating electricity is you connect a solenoid to a voltmeter or galvanometer. If you push a magnet into the solenoid, you will notice that the voltage is generated. Faster you push it in or pull it out, the bigger the voltage. But the problem is, not problem lah, the another observation is if you push it in the voltmeter one direction, you pull it out opposite direction. Okay, later we explain why lah. Third experiment that you can use is you have two magnets facing each other, then you place a wire in between them. If you push in or out of push it through or pull it out, the voltmeter will show you a reading. So faster you push in or pull out, the larger the voltage. And when you push it in and you pull it out opposite directions, the voltage will be opposite. So how do we explain all these phenomena? So this is the first part. So then you will describe this experiment in the exam. Later on you explain why. Okay. So according to Faraday's law, for an EMF to be induced, two things, either one of two things must happen. So he talks about cutting of flux or the change in flux linkage. There must be either one of these happening, then an EMF will be induced. So what is cutting of flux? What is change of flux linkage? Now, according to Faraday's law, what is cutting of flux? So let's imagine there is this magnet here. So you can see the magnetic field here. So surrounding let's say there is a wire, and you push the wire from outside the field towards the magnet. As the wire moves towards the magnet, can you imagine this wire here is cutting through the magnetic flux? So this is what it means by cutting of flux. And Faraday says because the conductor cuts a magnetic flux, there will be EMF induced in the conductor. So this is one of the things he's talking about. Another example of cutting of flux, let's say again you have this magnet with the magnetic flux around it, a magnetic field. If you bring a solenoid from outside to inside, as you push it in, wouldn't it be cutting the flux? Yes, so that can also cause an EMF to be induced in the coil. But there's another way of looking at it. We can talk about it in terms of change in flux linkage. Because when the coil is outside the field, there's no flux inside here, so there's no flux linkage. But when you bring it inside here, there'll be flux passing through the coil, so there's flux linkage. So there's a change in flux linkage which will cause an EMF to be induced. But usually, when do we use cutting of flux? When do we use change in flux linkage? Cutting of flux is used when there's relative motion between conductor and field. That means either this one moves or this one moves or both moves. Then we talk about cutting of flux. So here I would tend to use cutting of flux. When do we use change in flux linkage? Is when nothing moves. Example, in a transformer. Now in a transformer, the basic structure is a soft iron coil, and then you will have a primary coil here connected to a source of alternating voltage. Let's say we use a sinusoidal alternating voltage. And then the other one will be a secondary coil. So let's say we connect it to a resistor, right, to measure the voltage. So let's say we measure the voltage across here. Okay. Now, because this primary coil is connected to alternating voltage supply, that means the current will vary, right? So the current in your coil will be varying sinusoidally. So if it varies sinusoidally, the flux density in your solenoid, remember, is B equals to mu IN. So the B will be directly proportional to current. So that means the flux density will follow the same shape. So that means the flux in your solenoid here will vary with the current. And the soft iron core, being a soft having soft magnetic property, will be easily magnetized, right now. So the function of soft iron core is to concentrate the flux. That means how does it achieve it? It gets magnetized as well. When the soft iron core is in the magnetic field, it will be magnetized. So in other words, when it's magnetized, it will sort of modify the field of the solenoid, because without the soft iron core, then the field of a solenoid, remember you draw a middle line, then half will go here, then half will go here. But because the soft iron core is magnetized, it will transfer the flux. Most of the flux will be transferred to the secondary coil, because it goes one round, because the soft iron core is one round, that means the whole thing becomes magnetized. So it transfers the flux over the secondary. So when the flux here changes, this secondary coil experiences the change in flux. So because it experiences a change in flux, there's a change in flux linkage. So therefore, an EMF is induced in the secondary coil, which causes the current to flow. That's how you can measure the voltage. So this example is when there's nobody moving, but there's an EMF induced due to the change in flux linkage. That's when we use it. So what does Faraday say? So Faraday says either one of these will induce an EMF, but he also gives you the formula for the magnitude of the induced EMF. So if you look at the definition of the Faraday's law, Faraday says that the magnitude of the induced EMF is directly proportional to the rate of change of flux linkage, or you can say it's directly proportional to the rate of flux cutting. Either one. So it depends on the situation in the question. If there's relative motion, then they ask you to quote Faraday's law, then you use the flux cutting. If there's no relative motion in the transformer, for example, then you use the Faraday's law, but you mentioned about change in flux linkage. So if you go back to his definition, he says that the induced EMF is proportional to the rate of change, so ddt, of the flux linkage, which is n phi. So therefore, if you change it to equal, remember you must put a constant. Your constant is negative, so you get d and phi dt. But the negative is actually due to Lenz's law, so we can ignore the negative when we're calculating the magnitude. So when you talk about magnitude induced EMF, you don't have a negative. So when people look at this equation, they think they have to differentiate, but actually you don't have to. Our calculations are very simple in A levels. What we do is, to find the induced EMF, we just have to find the change in flux linkage. That means you use the formula for flux linkage, which is NBA, to calculate the initial flux linkage, and then calculate the final flux linkage. You subtract the two, you get the change in flux linkage, which is d n phi. You divide by the time taken, that's how you get your induced EMF. That's it. But when you're doing a conductor, cutting of a flux, there's a second equation which we can derive from here. Now let's say we are using this formula for solenoid. So when do we use this formula? Usually when we talk about a coil, and then initially there's a flux here, then we can find the change in flux linkage. Now when the conductor cuts a flux, we can actually modify this formula. Now let's say you have a magnetic field here, and let's draw the magnetic field, let's say, into the plane of paper. So this is a magnetic field into the plane of paper. And let's say our conductor is a straight conductor like this, and is traveling with speed v. The length of the conductor, let's give it L. So if I want to derive an equation from the Faraday's law, this is what I do. Faraday's law says the induced EMF is the rate of change of flux linkage. If the magnitude, do I put negative, right now? And since your n is 1, because it's one conductor with no turns, so I just put d phi dt without the n. So no need negative because of magnitude, no need the n because there's only one conductor here. So from here, remember the flux is also equals to BA. So I can take out the B and I get dA. Let's take out the B. Yeah, let me rewrite this. So I get B dA dt. Right now. So what is dA dt? dA dt can also refer to area swept per second. So how do you find the area swept per second? Now imagine this conductor here has a length L and it travels with a speed of V meter per second. V meter per second. That means in 1 second, it travels V meters forward. But this length is L. So that means in 1 second, its area that it sweeps is L times V. Agree? No? Agree? So therefore, the dA dt here will be the area swept per second, which is the length times the speed. So which is BLV. So for a conductor moving in a magnetic field, we can use this formula. BE equals to BLV as a shortcut. Otherwise, you have to find the flux that is cut, then you divide by the time. Also can. That means we still don't have the n, but we find the flux using BA first, the amount of flux being cut, then you divide by the time. which is a bit more tedious. This is a bit faster. So the formula for induced EMF gives you this, either this or the previous one. The unit for induced EMF will be volts. So you don't have any special units, it's still in volts.